So this week it is all about the standard normal distribution. So we're going to start off talking about just the normal distribution. Now, it doesn't seem like there should be much difference between a standard normal and a normal, but there is a little bit. A normal distribution just means that it's a continuous distribution, meaning it's going to be from measurement, usually time or temperature or actual measurement. And it is widely used and also widely abused. It's the bell-shaped curve, and you see it in all disciplines, science, business, mathematics. An example is, if you ask enough people their shoe size, you will find that the graph data is like a bell-shaped curve. Now in the middle, you're going to have your mean, okay? And then it will go down from there to the outliers, meaning the kind of odd size. Maybe somebody has an extremely small foot, someone has an extremely large foot. Those are going to be the outliers. But your data is going to be grouped around the center, around the mean with some variation. And as we talked about briefly, the empirical rule will come into play this week, where we're talking about what percent of the data is close to the mean, and then a little further out and a little further out. And we're going to use standard deviations as our measuring going out. Remember, one standard deviation on either side of the mean captures about 68% of our data. Two standard deviations on either side of the mean captures 95% of our data. And three standard deviations is just about all. 99.7 is what it's usually termed to be of our data, meaning that there might be something out there that is not included in the data set once I reach three standard deviations, but it is going to be just about all. So knowing that, we can use that to compare this data set against this data set, which one has the most variation, which one has the larger variation, and those kind of things. So that's where we're going this week. What does this look like? Well, it looks like a little bell curve, right? This is a normal distribution. We're not to standard normal yet. This is just the normal distribution. And it has just two parameters in it. It's going to have the mean, which is mu, and the standard deviation. So when we're talking and have problems about a standard, I almost said standard normal. Nope, just the normal distribution. We're going to be talking about the mean and standard deviation of that. This might be a little confusing, but we're talking about x is a quantity to be measured that has a normal distribution. So in that previous example, it was shoe size, right? X would be the shoe size. And it has a normal distribution with a mean of mu and a standard deviation. This is kind of how we write it. Instead of in words, that's how we would write it without words, in notation. I'm going to move this down because you don't need to see the title anymore, and I'll show you all this lovely math that you do not have to learn. And if I can get my thing to slide down. It slides down when I don't want it to, but when I want it to, it doesn't. There we go. Okay. This is the math that is going to describe the shape of this function. Okay. You don't have to learn it. It is done. We're going to do a lot of calculator work, and it will be done inside the calculator. Remember that E is an actual number. As you look at this, we know that pi is a number. We have our standard deviation we can plug in, and we have our x and our mu. So these are all numbers that we can plug in if we wanted to, but it is quite an intense formula. So rather than do that, I just want you to be aware that it is there. Again, the normal distribution just has those two parameters. The probability density function, that would just follow this line, and I won't be able to draw it nearly as well, right? Freehand. That is what this function gives you. Whoa, it's interesting, the whole thing moved. This function right here gives you that curve. Here, this is just showing that the curve is symmetrical, and a vertical line can be drawn through the mean. In this case, we're using these parameters here. So if I draw a line through the mean, maybe right about here, whoa, crooked line through the mean. That's what it's describing, okay? The line through the mean. A change of this mean causes the graph to shift from left to right. That makes sense. If my mean was over here, then it would be rounded over there, right? When we are talking about all these, we have all these possibilities of normal distributions. We are going to try to normalize that so that we can use the same mathematical principles on all of our distributions that fall into this category. And that is what we call our standard normal. I'm going to just slide this up a little bit for now. Standard normal distribution is going to be a normal distribution, but we're going to say, we're going to normalize it and say that our mean in this particular one is 0. Now we will have a mean from our problem, whatever data we have. But when we put it into this standard normal distribution, our mean is going to be 0 and our standard deviation is going to be 1. So we go a -1 and a +1 outside of that, and then 2 and 3. That way we can normalize it. And here's an example, and it talks about the z-score, which is 3, meaning 3 standard deviations from the mean. So I can use that with any set of data, any normal distribution. If I know that my z-score is 3, and in my problem my mean is 2 and a standard deviation is 1, well, I would add 3 to that 2 to get the outer limit, and subtract 3 and get a -1 for that lower limit. So I'm normalizing all of my normal distributions into this standard normal distribution where I'm going to be using these z-scores and a mu of 0. To find an actual z-score number, I would take the point that I am interested in, subtract the mean, divide it by the standard deviation, and that's what gives me the z-score. And it is written like this over here, where my standard deviation is 1 and my mean is 0. Now I just want to kind of say what we're, just show up a picture here, drawn not very well, with my mean coming down the middle. If I'm talking about this, what this is saying is, okay, I'm interested in this point. Let me draw the bottom line here. I'm interested in this point here. Okay, this is my x. Whatever this is, let's say it's shoe size again, okay? What's the probability of a shoe size of, oh, I'm going to guess that the mean was this. What's the probability that someone will have a shoe size greater than 9? So if I do this, remember probability is the area under a curve. I'm interested in this area here. So just not to get into the math right now, but what this is saying here is that I'm going to take this x, that's where x comes in, and I'm going to subtract the mu, and I would get a 2. And I would divide that by my standard deviation to see how far away I am from that mean. So that's kind of a bare bones approach to explaining what the z-score actually means. Here we have a normal distribution, standard normal, because I have 0 and 1, and it is right on my axis, okay, because 0 is my standard deviation. Excuse me. So let's look at an example. The first example is just how to find a z-score. So what is the z-score of x? When x is 1, and then we have that notation. We have a normal distribution, and remember we have our mu listed first, so our mu is going to be 12 and our standard deviation is 3. We just run that through that, grab a pen, run that through the formula, and we end up with this number, meaning the z-score of x is a -3.67. Okay, what does that kind of mean? Oh, let's go back to our little normal curve. We draw lots of pictures in this section. Here's my mean. This is going to be this direction, right? It's a negative number. It's a -3.67. So we're talking about a section that's going to be something like this. It doesn't tell us whether we're trying to solve for this area or this area, but it doesn't matter. What we're talking about is a z-score that is going to be over in the negative direction. That's the part that they wanted us to make sure we understood. This next example, some doctors believe that you can lose 5 pounds on the average a month. by reducing their fat intake and exercising. So the weight loss is a normal distribution, and X is going to be the amount of weight lost in pounds by a person a month. So use a standard deviation of 2 pounds. So that is what this notation is telling us right here. We have the average weight loss. Average is going to be our expected value, which is going to be our mu. And then we have 2 as our standard deviation. So knowing that information, let's go down here. Suppose a person lost 10 pounds a month. Okay, the Z-score when X is 10 is 2.5. How do we know that? Well, we just use this formula right there. Okay, since it's 2.5, we know, I'm going to just do a little bell over here. 2.5 is going to be 1, 2, and a little bit. It's going to be way out here, right? So losing 10 pounds is quite above our mean or our expected amount. Okay, so the Z-score tells you that X is 10 is how many standard deviations? 2.5 standard deviations, right? I had to come out 2.5 standard deviations to the right of our mean. And what is the mean? Well, we go back to that mean being 5. It's given up here in the problem. Okay, and this tells you all that I just did in the scribbles. So hopefully that part makes sense. It's starting to click a little bit how we use this idea of a Z-score for a standard normal. Using that same problem with the fat intake and all that, and we're given that same notation. Let us suppose that a person gained 3 pounds. Okay, now gaining 3 pounds is going to be a negative weight loss. So our X is now -3. Okay, what is Z going to be then? And what does the Z-score tell us? Okay, so maybe we need to go back here and look at our formula again. Right here, X minus mu divided by standard deviation. So X in this case is -3. So we have -3, 3 minus our mu, which is 5, which gives me a -8. And we're going to divide that by standard deviation, which is 2. So therefore, we have a Z-score of a -4. The Z-score tells you that X of -3, that was how much they actually gained. Okay, so a person gaining 3 pounds when they've reduced fat and are exercising more, it's actually 4 standard deviations to the left of the mean. That means it's not very likely. Remember, almost all of our data is within 3 standard deviations. 1, 2, 3. So it means it's way out here as an outlier. And we're going to go 1, 2, and 3 on the positive direction also. So it is not very likely that you would gain 3 pounds if you were following this advice. Let's just look at another example using the same data. Here we still have that 5 and 2. Suppose random variables x and y have the following normal distributions. Right here and here. If x is 17, then z is 2. We can do that by doing the math, right? This was previously shown. If y is 4, what is z? Well, if we put y is 4 in here, it's right in here. 4 minus our 2 divided by 1 gives us 2. Okay, so 17 is going to be put into this equation over on this side. 17 minus 5 divided by 6 is how you get the 2, if you were confused about that. Just using our Z-score formula. That is what those problems are about. Just a little bit more on this one. Empirical rule. I've stated it a couple times. Here's just a in black and white for you, so you don't have to just remember it. Excuse me, for what I've said. This is a good reminder of our empirical rule, and we can use the empirical rule Again, with our z-scores, we know that we'll have 1 and -1, 2 and -2, and it follows that same percentage. We can use the empirical rule in something like this. X has a normal distribution with a mean of 50 and a standard deviation of 6. About 68% of the X values lie within one standard deviation. So we can take that standard deviation of 6 and add it to 50 and then subtract it from 50 to get what my lower value and upper value are here. So we would have 44 to 56 would contain 68% of all of my scores. This is pretty powerful and a really quick way to do some nice calculations. Another example, same standard deviation and mean. About 95% would be then within 2 of these, all the way across here. So what is my lower and what is my upper limit? Well, 2 standard deviations would be just 2 times 6, so it would be 12. I would add 12 to this, getting a 62, and then I would subtract 12 from it. So there's my 62, there's my 38. Those are my limits then. All of the data, 95% of the data, is between 38 and 62. So that is kind of how we can use our z-scores and the empirical rule to make some good judgments about our data. I think there's just one more, just talking about 99.7. Of course, that's 3 standard deviations. So we would do 3 times 6, which would give me 18, adding that to 50 and subtracting it from 50. I would get my inside and outside from that, 32 and 68. So just a nice way to use the empirical rule. I hope there just wasn't too much here. Let me know if you have some questions. Thanks.